Hello students, today let us work out the problems from chapter 4, Moving Charges and Magnetism. The first question, a circular coil of wire consisting of 100 turns, each of radius 8.0 centimeter, carries a current of 0.40 ampere. What is the magnitude of the magnetic field B at the center of the coil? Now here we have a circular coil of wire and this coil consists of 100 turns. So N will be 100, each of radius 8.0 centimeter. This is the radius of the coil, and since it is given in centimeter, you have to convert it into meters. So 8 into 10 to the power minus 2 meters or 0.08 meters. And it carries a current of 0.40 ampere. Current is represented by the letter I. Now we have to find the magnitude of the magnetic field B at the center of the coil. So the formula, as you know, for magnitude of B is mu 0 by 4 pi 2 pi Ni by R. Mu 0 stands for permeability of free space, and its value is 4 pi into 10 to the power minus 7 Tesla meter per ampere. So when you work out the calculation with the data given, you get your answer to be 3.14 into 10 to the power minus 4 Tesla. Next question. A long straight wire carries a current of 35 amperes. What is the magnitude of the field B at a point 20 centimeter from the wire? Now this is an application of Biot-Savart law, and you get the formula for magnitude of the magnetic field as B equal to mu 0 by 4 pi 2I by R, or you can write it as mu 0 I by 2 pi R. Now mu 0 has a value 4 pi into 10 to the power minus 7 Tesla meter per ampere, and therefore when you substitute the values, you have the value of current I as 35 ampere and R as 20 centimeter, which you have to convert it into meters. So you get your final answer to be 3.5 into 10 to the power minus 5 Tesla. Next question. A long straight wire in the horizontal plane carries a current of 50 ampere in north to south direction. Give the magnitude and direction of B at a point 2.5 meter east of the wire. So we have a long straight wire in a horizontal plane carrying a current of 50 ampere from north to south. And we have to find what is the magnetic field at a point 2.5 meter east of the wire. Now, if you apply the formula for magnetic field, you know it is mu 0 I by 2 pi R. Or for the sake of cancelling, that is mu 0 value is 4 pi into 10 to the power minus 7, and we give a denominator 4 pi with a 2 as the numerator, so that you get the magnitude of B as 4 into 10 to the power minus 6 Tesla. Let us see what is the direction of B. So here we have north to south, that is the direction of current. Now east, 2.5 meters east, what will be the direction of the magnetic field? So here we must apply the right hand thumb rule. When you use the right hand thumb rule, your thumb must point in the downward direction and the fingers will curl in the upward direction, this side of the axis north south, and it will be in the downward direction here. So we can say the direction of magnitude of magnetic field 2.5 meters eastwards will be in the upward direction. Next question. A horizontal overhead power line carries a current of 90 amperes in east to west direction. What is the magnitude and direction of the magnetic field due to the current 1.5 meter below the line? Now, just like the previous problem, you can find what is the magnitude of the magnetic field using the formula, because this is for a straight wire. So B equal to mu 0 I by 2 pi r, or mu 0 into 2I by 4 pi r. And when you use this, substitute the values, you'll get your answer for magnitude to be 1.2 into 10 to the power minus 5 Tesla. What about the direction? Here we have the current flowing from east to west. And the point under consideration is 1.5 meters below the power line. So when you apply Maxwell's right-hand thumb rule, the direction of magnetic field will be towards the south. So below, so where is it pointing? It is pointing below, so then it will be south direction. The next question. What is the magnitude of magnetic force per unit length on a wire carrying a current of 8 amperes and making an angle of 30 degrees with the direction of a uniform magnetic field of 0.15 Tesla? So this is a direct formula. You know magnetic force per unit length of a wire is given by F equal to Bi sine theta. So there is an L here. That L has been taken to the left side as force per length, because the question is force per unit length. So here on the right side we will have only Bi and sine theta, whereas on the left side it is capital F by L. So now let us make the substitute the values, and you know sine 30 value is 0.5, so your final answer will be 0.6 Newton per meter. Next question. A 3.0 centimeter wire carrying a current of 10 ampere is placed inside a solenoid perpendicular to its axis. The magnetic field inside the solenoid is given to be 0.27 Tesla. What is the magnetic force on the wire? So magnetic force exerted on the entire wire is given by F equal to BIL sine theta. So B value is 0.27 Tesla, I is given as 10 ampere, L is given as 3 centimeter, which you will have to convert into meters by multiplying it with 10 to the power minus 2. And theta, of course, is given as 30 degrees. Sorry, 90 degrees, because it is perpendicular to its axis. So sine 90 degree is 1. Therefore, you get an answer 8.1 into 10 to the power minus 2 Newton. We are finding out force, so the unit will be Newton. Next question. Two long and parallel straight wires A and B carrying currents of 8.0 ampere and 5.0 ampere in the same direction are separated by a distance of 4.0 centimeter. Estimate the force on a 10 centimeter section of wire A. Now here also the formula is direct. F equal to mu 0 Ia Ib into L by 2 pi r. So for ease of calculation, we are bringing the denominator as 4 pi, and here you are multiplying it with a 2, so that this 4 pi and this 4 pi will cancel on its own. So when you substitute the values of Ia, that is 8 ampere, Ib is 5 ampere, L is 10 centimeter. L is 10 centimeter section of the wire, and R is 4 centimeter. So 10 and 4 you have to convert into meters and then continue with your calculation. You get your force to be 2 into 10 to the power minus 5 Newton. And if you remember the theory, two long parallel straight wires carrying current will exert a force, and the force will be attractive if the current is in the same direction, and the force will be repulsive if the current is in the opposite direction. Here we have current in the same direction, and therefore the force will be attractive. Next question. A closely wound solenoid 80 centimeter long has 5 layers of windings of 400 turns each. The diameter of the solenoid is 1.8 centimeter. If the current carried is 8 ampere, estimate the magnitude of B inside the solenoid near its center. Now, solenoid magnetic field inside the center of the solenoid. By Ampere circuital law, we have done the calculation for B equal to mu 0 Ni by L, where capital N gives you the total number of turns. So we have 5 layers with 400 turns each. So the total number of turns will be 5 into 400, that is 2000. So capital N will be 2000. And these 2000 turns exist in a 80 centimeter long wire. So the length of the solenoid is 80 centimeter. So the number of turns per unit length will be 2000 by 0.8. And therefore, you can do the calculation, rest of the substitutions, and you get your answer to be 2.512 into 10 to the power minus 2 Tesla. The next problem. A square coil of side 10 centimeter consists of 20 turns and carries a current of 12 ampere. The coil is suspended vertically and the normal to the plane of the coil makes an angle 30 degree with the direction of a uniform horizontal magnetic field of magnitude 0.80 Tesla. What is the magnitude of torque experienced by the coil? So we have a very direct formula for torque. Torque is equal to NBIA sine theta. So N stands for the number of turns that is given in the question as 20. B stands for the strength of magnetic field which is given as 0.80 Tesla. I is the current that is 12 ampere. A is the area of the coil. Only the side is given as 10 centimeters. So you have to find the area of the coil 10 into 10 and convert it into meters, square meters. So here we get 0.01 square meter as the area of the coil. And of course, theta is given as 30 degrees here. So sine 30, you know, is half. So when you make the substitutions for the values, you get your answer to be 0.96 Newton meter. Okay, thank you, students. We'll continue our problems in the next part.